What is the relationship between the speed of the object tangent to the circle and the angular velocity, omega? It turns out that's an important relationship. Let's sketch another diagram and see what that relationship is. Let's suppose that we begin with our object at the origin, say, of our angular coordinate system. And let's say that it has some tangential speed v parallel. Now, at some later time t, the object is going to have gone around the circle so that it is now at a different position, and it has tangential speed at that point. The object has passed through some angle theta, or delta theta if you would like. We are trying to relate omega and v with each other. The object has passed through some arc length that we'll call s. We can say that the average tangential speed is going to be equal to the distance that it's traveled along the perimeter divided by the amount of time that it's taken to travel that distance. Now, if the object has been traveling the same distance away from the center of the circle, then there's a relationship between this arc length delta s and the angle in radians delta theta through which that object has passed. That's the arc length relationship that says delta s is equal to r times delta theta. Let's put that relationship into the linear or tangential speed relationship. When I make that substitution, I get that v is equal to r delta theta divided by delta t. But now, what is delta theta delta t? That's equal to the angular velocity, or the magnitude of the angular velocity. Let's make that substitution so that finally we're going to end up with a relationship that tells us that v tangential, or the linear speed, is equal to r, the radius, times the angular speed. That is going to be a very important relationship. This is the relationship between linear speed, tangent to the circle, and angular speed. In a similar way, we can talk about angular acceleration. And there's another animation to show.
A point undergoes an angular acceleration, alpha, when its angular velocity changes in time. Angular acceleration is a vector. Its magnitude is proportional to the rate at which the angular velocity is changing. The tangential component of the object's linear acceleration vector is tangent to the object's path. Its magnitude is r times the magnitude of the angular acceleration. The angular acceleration vector points along the axis of rotation and is given by the right-hand rule. When the disk's angular speed increases, the angular acceleration is in the same direction as the angular velocity. When the disk's rotation slows, they are in opposite directions. It stops for an instant and then begins to spin in the opposite direction, and the vectors change accordingly. Alpha is expressed in units of radians per second squared.
Angular acceleration is indicated by the Greek letter alpha, and it's defined to be the rate at which angular velocity changes, delta omega delta t. We can see the relationship between angular acceleration and linear or tangential acceleration. So let's suppose that I have some initial tangential velocity here, which I'll call v parallel initial. And when the object actually spins up faster or slower, it's going to change its tangential speed. So at some time later, it's going to have a different tangential speed. Let's call that the parallel final. Because the tangential speed changed, then we can talk about a tangential acceleration. The tangential acceleration in magnitude is going to be the change in the tangential speed with respect to time. So in our diagram, that's going to be the final tangential speed minus the initial tangential speed divided by the time interval of interest. But what is the tangential speed? The tangential speed is equal to r times the angular speed. So I could make a substitution in here, r times omega for each of the speeds. If the radius is constant, I can factor that out, so that I'm going to have r times omega final minus omega initial divided by delta t. But the change in the angular velocity is equal to delta omega delta t. That's what alpha is. So here is the final relationship. The tangential acceleration is equal to r times the angular acceleration. And that is a very important relationship. That, along with the definition of angular acceleration delta omega delta t. These relationships for omega and alpha basically are good for objects that are spinning. So I have some solid object that's spinning around its axis, and we're describing that sort of motion. This is good for flywheels, for any kind of rotational motion that happens in a solid object. It turns out that there is a relationship between the linear equations of motion under constant linear acceleration and the angular equations of motion. I've written these linear equations of motion without subscripts, but I want to add some subscripts now, and I want to talk about tangential velocity. So I'm going to put tangential indications there, those parallel bars, to indicate that this is motion along some perimeter of a circle. And this acceleration is going to be tangential acceleration. Instead of writing x's or y's for distances, I've written s for arc length. So when we talk about arc length, we can talk about final position and initial position, tangential speed, and tangential acceleration. And likewise, we can include these tangential bars here in each of these symbols here. Now there's a relationship between these things and their angular counterparts. So if you'll recall, we've said that s, arc length, is equal to r times theta, where theta is the angle in radians through which the arc length passes. We've said that the tangential speed is equal to r times omega, where omega is the angular velocity. We have said that the tangential acceleration is equal to r times alpha, the angular acceleration. And you remember we've said that omega is delta theta delta t, and that alpha is delta omega delta t. So now with these things, we could actually make a whole series of substitutions and write an angular set of equations of motion. I'm not going to actually go through the algebra to solve them, but I do want to write down what the equations are. There are three analogous angular equations of motion under constant angular acceleration. Omega is omega naught plus alpha times t. Theta is theta naught plus omega naught t plus 1/2 alpha t squared. Omega squared is omega naught squared plus 2 alpha times theta minus theta naught. And just for kicks, let's see where one of these comes from. So V parallel is V naught parallel plus alpha parallel times t. That's the first equation of motion. But let's recall that V parallel is r times omega, and alpha parallel is r times alpha. So if I make those substitutions, so we'll say r times omega is equal to r times omega naught plus r times alpha t. And now I have common factors of r's that will divide out, so that omega is equal to omega naught plus alpha times t. So that's where these equations come from. Now let's take a look at some numerical examples. Example 55.3. A wheel has a radius of 2.0 meters. It begins from rest, spinning with constant angular acceleration of 2.5 radians per second squared. A. Determine the linear distance traveled by a point on the outside edge of the wheel in 5 seconds. B. Determine the linear speed of a point on the outer edge of a wheel after 5.0 seconds. C. how many revolutions did the wheel make in 5.0 seconds? Now, if you want to, you could think about this as a carousel, the Coolidge Park carousel, or some other spinning object. I like to sketch diagrams for these. Let's suppose that this black object sitting on the plus x axis is the initial position of this wheel. And this object is now going to be moving around in a circle as the object spins up. They tell us that the angular acceleration is 2.5 radians per second squared. So this object is going to be moving in a circular path and picking up linear speed as it does so. We're trying to figure out the linear distance traveled by the point on the outer edge of the wheel in 5 seconds. Well, there are several ways you could approach this. You could say that the linear acceleration A is going to be the angular acceleration alpha times r. So this tangential acceleration is going to be 5 meters per second squared. It starts from rest, and so we can say that the initial angular speed is equal to 0, which means that the initial linear speed is also going to be equal to 0. Now I know what the time is, 5 seconds, so I could write a linear equation of motion. The linear equation of motion says that S is going to be equal to S naught plus V naught times t plus 1/2 a t squared. If we let our initial position S naught be equal to the origin, in other words the place where the action begins, then the initial term and the velocity term, the initial velocity term, disappear, and now I can just put in the numbers. So I get that the distance that the object travels around the circle is 62.5 meters. And now here's what this means. As the object goes around the perimeter of the circle, let's say it ends up at this spot over here at the edge, then what ends up happening is it travels a distance of 62.5 meters. Well, how fast is the object going to be moving in linear motion? We've got the things that we need up here with the initial tangential speed and the angular acceleration, the linear acceleration, and we can write that. We can say that V is equal to V naught plus A times t. And since V naught is 0 because the object starts from rest, then we can just put in the numbers. So after 5 seconds, the object is traveling at a speed of 25 meters per second. So you could say here that the tangential speed after 5 seconds is 25 meters per second. That's how much distance per time the object is covering when the object has been moving for 5 seconds. Now, what about the number of revolutions that are made in 5 seconds? To figure this out, I need to relate the fact that revolutions and angle are going to be related to each other because there's 1 revolution in 2 pi radians. So if I could figure out the angular distance that the object travels in 5 seconds, then I could convert that into revolutions. So I'm going to use the angular equation of motion. Theta is theta naught plus omega naught times t plus 1/2 alpha t squared. And recognize that theta naught is 0, in other words I'm starting at the origin, and that omega naught is 0 because I'm starting from rest. And now I can just put in the numbers. In radians, I get that the object has spun through 31¼ radians. But what I want to know is how many revolutions is that equal to. So I need to convert that angle into revolutions using my conversion factor. And I get that after 2 seconds the object has spun through just under 5 revolutions. Here's what the picture looks like. The object starts from rest at the origin. Now it spins through 1, 2, 3, 4, almost 5 revolutions here in 2 seconds. So the object is spinning up, it's gaining angular speed. That's the first example.